Welcome to Ask and Learn.
Okay, so this question is asking why, if you have a gas in a high pressure cylinder, if you suddenly open it, why might, let's see, they ask specifically condensation. Okay, why does condensation happen? And then the question gives a few options. So I'm drawing the cylinder, and then here's kind of a hole, and then here's my representation of the particles sort of rushing out, kind of expanding. So I did think about this one a little bit because it's kind of unique in that not many of these questions sort of ask about sudden changes or kind of out of equilibrium physics. So I personally like to think about thermodynamics on a microscopic scale and then figure out how that translates to macroscopic quantities. And it's kind of different. I don't think I see it a lot in the books, but I think it makes the most sense to me. So I'm going to think about this on a particle to particle sort of perspective. So you have this gas rushing out, and then it's rushing out presumably into the atmosphere, which I'm going to represent with these red dots. So the atmosphere particles are kind of all going at some whatever speed corresponds to room temperature, and they're exerting pressure on the gas in some sense, even though they're not really like a container. They are still pushing the gas inward. They're still pushing the gas inward. And so, for example, if there was no atmosphere, then the gas would just expand more quickly. And so thinking about it on this microscopic scale, imagine you have this atmospheric particle, and then let's say you have a particle from the high pressure container sort of lunging at it. I'm thinking of this as from the perspective of just kind of treating them as two pool balls or something, two spheres. And if they collide, the gas, the NO2, or what was it? N2O. It's going to transfer some of its momentum to the atmospheric pressure, to the atmospheric particle. So I'm just going to write that down. Rad equals atmosphere Okay, just to make sure I'm being totally clear and not just saying a bunch of stuff that doesn't make sense. And then the black is equal to the N2O. Okay, so yeah, so you have the black particle, it's expanding, hitting the red particle, and it's gonna transfer some of its kinetic energy. And so then the N2O gas is gonna have maybe less kinetic energy. And so that to me would be a reason why it would get colder and thus condense. And so how do we put this microscopic process in the language of thermodynamics, sort of a macroscopic perspective? I think that the D makes the most sense. So the gas is doing work. So yes, the gas is kind of exerting a force on the atmospheric particles. So that makes sense. And there is no heat input. And I think that also makes sense. So there's not an external source heating it. So I think that explanation makes the most sense. And then just to show that implies that the temperature is decreasing and thus condensation is occurring, I'm just going to explicitly write out the equation that would show that. So we have our equation that I'm sure you've seen many times if you've been doing these problems. The change in internal energy is heat added plus the work done on the gas. And then so Q minus the integral of P dV, or just PV, I don't know if this uses calculus or not. And so, yeah, so if we say that the gas is, actually, I guess there's a couple ways to think about it. I'm just going to ramble on too. The first way would be to think about this as like, this dV is sort of going up, right? And then the pressure would be the pressure from the due to the collisions with the atmospheric gas, so it would be atmospheric pressure. But anyway, this term is non-zero, but it's negative. And if we say that there's no heat being added to the gas, this term goes away. Then you get that delta U equals, some negative number. So i.e. delta U is decreasing. The other way to think about it too is like, I'm not sure if you've seen this or not, but this integral of PdV as a quantity for work, it's kind of the same thing as like force dotted with distance. And so you can see sort of from this perspective that this particle, the black particle, is exerting a force on the red particle. It's a force kind of up, and then in the way that I drew it, and then the displacement would be up. And so there would, this term, integral term, would be positive, and then it has a negative out front. That's why it's negative. And so, yeah, that's just another way to think about this problem. So hopefully